Hi there, and welcome back to our video lecture in ENSC 106. And in this video, we'll be starting our first topic, and the title is Review of Static Concepts. So, as I've already said, that in studying the strength of materials, we need to have a solid foundations about equilibrium and how to find the support reactions and things like that. Okay, so in this video, um, we'll be reviewing the idealization of forces, support reactions, and then we will solve problems, equilibrium problems, and things like that later. Okay, so uh, let's recall or let's have an overview of the mechanics subject. So mechanics basically is a subject that deals with forces and the body's response. Okay, body's response to that force. Okay, so for example, I have a body right here and I apply a force. Okay, so let's say this is the initial position, and after or because of this application of forces, then it changes its position right here. Let's say this is delta S. Okay, so because of that force, then there's a change in position. And another possibility is that, so let's say we will try to provide a stopper or a stopping block right here, and when we apply force, is instead of having a translation or a linear translation, it another possible response is that it can have, or it can be some it can uh, move, or it can rotate something like this, right? So this is our delta S, but this delta S is in terms of angle. Okay, so this one is in terms of linear, and this one is in terms of angular motion. Okay, so if the body's response is, we can have um, we can have this, and this is what I call a motion response. But there's also another response, like for example, there's a beam, and then we just want to solve for the internal forces or the support reactions right here. Okay, so if that's what we want, then I call this as, and by the way, there should be a force, right? So let's say it's subjected to an external force. Okay, and because of this external force, then support reactions are generated, and this beam is not in motion. Okay, so the response is just simply a static response. Okay, whereas in these two examples right here, the response is in terms of motion. And when we say static response, that's the concern of the subject called engineering statics. And right here, for the motion response, this is the concern of engineering dynamics. And of course, there are other topics like, for example, the moment of inertia or mass moment of inertia. Okay, but the main idea is that if you're dealing with static response, then that's the concern of engineering statics. Motion response, that's the concern of engineering dynamics. So, if you recall that in these two subjects, we assume that a body is rigid. And when we say rigid body, if this is our body, and then we try to locate some points, or we try to make some grids. Okay, and let's say this is the point. All right, so once the force is applied on this body, okay, so once that force is applied, if there's a change in terms of the linear distance or angular distance, so let's say instead of initially we have these points, but then after the application of force, it changed to something like this. Okay, so it compressed, or it could be there's a change in terms of the angle. Okay, so if there's changes in the distance, in the linear distance or the angular distance, then that's what you call a non-rigid body. Okay, non-rigid body. Okay, and of course there are applications wherein we can use this rigid body assumption, um, if we are considering, or if the loads, if the applied loads is within the elastic range or far from its limit, yielding, I mean far from its specified strength, then of course we can assume a rigid body. And we also discussed that in engineering dynamics, that for example, if the geometry of motion is far greater, okay, or is far larger than the than the geometry of the body itself, so we can just analyze something like a point mass, or something like a rigid body, or things like that. Okay, but of course, in real world, every material has only a specified strength, and there's a limit that when you apply too much loads, then it's going to break apart. Okay, so that depends upon the type of problems, and the type of assumptions that we will have. Okay, so another response is that, for example, I have this bar right here, and then I subject this bar into tension forces. So I'm trying to pull this bar apart. Okay, so what will happen is that this bar will elongate. Okay, so originally this is the length, right? So L sub O, but then right here there's going to be some elongation, and let's use the symbol delta. Okay, so in other words, in this type of scenario, or in this type of example, we are now considering the deformation, or we are now dealing with deformable bodies. And when when we talk about deformation response, that's okay, that's the concern of the subject, called strength of materials, or mechanic of materials, or mechanics of deformable bodies. Okay, so that's it. So we are in this situation. Okay, so now before we can analyze the deformations and the internal forces, then let's review our idealizations about forces and moments. Okay, so recall that force and moments, there is something like an external agent that causes changes on the body, and as I've said, that change could be in terms of deformation or static conditions or deformation. Okay, so forces, we already know that the unit force, this is in Newton, right? And in terms of English units, this is pounds. And of course, if you're using SI units, then the prefix comes into play, like for example, kilonewtons, mega newton, or things like that. And right here, okay, so let's write here, okay, prefix. But right here, there's also another one. It's pounds, but sometimes you'll encounter the unit kips, which means kilo in pounds. So that's just 1,000 pounds. Okay, so just take note of these two units, two typical units for forces. And when we say moments, the unit of this moment is, okay, the unit of moment is force times distance, Newton meter, or um, in terms of English units, it could be pound foot or pound inch. Okay, and take note that um, this moment is can be described as something like a force that causes rotation. Okay, so if this is our body, for example, right? And let's say this is our center of moments or center of rotation, or let's say we are we are putting a hinge right here. And if I try to apply a force right here, so this force, if you notice that this force is eccentric to the center of moment. Okay, so because of this perpendicular distance or this eccentricity, there's the effect is that there's gonna be a rotation. Okay, so this is rotation. Okay, and take note this is force times the moment arm. So sometimes you just use R or X or Y, that depends upon the axis. Okay, but the point here is that the force is perpendicular to the distance. Okay, and also note that this unit of Newton meter, this it's also the same unit for energy, because for example, if we are going to push a body right here, so let's say this is our force, and then let's say this is our point one, and then it moved to point two, right? So we have delta S. We have a change of position. This is our distance, but you would notice this is also force times distance, except that the force is parallel to the distance, right? So that's the unit for work. Okay, that's the unit for work. But this one, this is moment, right? And sometimes, depending upon the axis of rotation, there's a specific term such as torque. Okay, so I guess we should have or we should differentiate it right here. So let's say this is my this is our body or our material, and let's say this is our x-axis, this is our y, and then this is our z-axis. Okay, so if the force, let's say if the force is along this, or if the force is causing rotation along the x-axis, then that's what you call torque. Okay, and although it's, I mean, the more general term is the moment. Um, it's actually the rotation is along the longitudinal axis. Anyway, we'll discuss that in detail when we talk about, or when we reach the topic on internal forces. Okay, so now how do we analyze the forces, or how do we analyze the moments? If we want to analyze them in, let's say in, I mean, when we do the computations, then of course we need idealizations. Okay, so how do we idealize? So number one, we can idealize force as a concentrated force, meaning that force is acting at a point, concentrated force. Okay, and by the way, force, we use a, actually force is a vector, and in symbol we use an arrow line. Okay, so that indicates the direction. Recall that when you say it's a vector, then that means it has a magnitude plus it has a direction. Okay, so for our first idealization, we said that we can idealize force as concentrated force if that force is acting at a point. Okay, so the, in figure, it's just something like that. It's just something like this. And another one is we can idealize force as line forces or line loads. Okay, so that means that a force is acting along a line. And another one is we can also have surface forces or surface loads. Okay, so that means that force can act along a surface or on a surface. So this is an area, right? So this is an area, this is a line, right? And this is a point. Okay, and therefore the unit of this for concentrated force, this is Newton. This is Newton per meter, and this one is Newton per meter squared. Okay, so so where do we see this in real applications? For concentrated force, if the area is so small compared to the other geometry, then we can assume that a force is a concentrated force. So for example, um, an example of this um, is if we have a beam. Okay, so if we have a beam and this beam is resting on a column. So in this example, the beam is resting on the column. So right here, the support reactions or the reaction of the beam is actually idealized as a concentrated force. Okay, so if there's a support reactions, then of course there must be some, let's say there must be some external forces. Okay, another example is the meshing of the gear teeth. Right, so these are uh, gear teeth. Yes, and right here we'll draw the what do you call this? The pitch circle. Okay, so the forces are transferred. Okay, because of this, or the forces are transferred from this gear to the other gear by point contact. Okay, so let's say this is the force. So this force is a concentrated force. Okay, now for the line forces, so the line forces, it's Newton per meter. Is an example of that is the weight of the beam. Okay, so for example, this is the beam, and because this beam has a unit weight and it has a volume, then of course there's gonna be a distribution of forces or of weight. Okay, so this is a line forces, and for the surface loads, this is typical for wind that's acting on a building, and also for buoyant forces or the forces that acts on I mean the hydrostatic forces. Okay, so right here, let's say this is the forces from the wind. Okay, so it's acting on an area. Okay, so I'm drawing right here. Um, force distribution from the wind. Although the wind is just acting on one side, if I draw the if I draw this in top view, okay, so let's say this is the front, right? This is the front. So let's say this is the front, this one. So even if the wind is just acting on this side, there's going to be an effect on the other sides, right? So there's going to be a suction pressure on this side, on the other sides. Okay, so uh, we'll not delve into the details of these surface forces. Okay, and for the moments, we can also have concentrated moments. So that means that if this distance is so small that we can neglect it, then we can um, we can we can assume or we can idealize that this force is a concentrated moments. Okay, and if that's the case, if it's a concentrated moments, then the unit would be Newton uh, Newton meter. All right. Um, Now let's move on to the support reactions. Okay, so the topic of support reactions is actually uh, an idealization because of, for example, an a frame buildings, right? So let's say we have a frame buildings right here. When I say frame buildings, it's just composed of frames. So let's say we have beams and we also have columns right here, and then another beams, for example. Okay, and let's say we have footing, right? And also if we want to put braces, cross braces, and things like that. Now if we want to see this beam, for example, then this beam is being supported by the column. Okay, so because of the presence of the column, I mean, somehow this column acts as a support to this beam. Okay, so that's why you recall that sometimes we idealize this pin roller support for the beams. Okay, so basically it's just something like an idealization of how will you analyze, okay, the building. Okay, so because right here we will have support reactions, so that support reactions will be transmitted to the next member. Okay, so basically the idea is that because structures are composed of many individual members that is also connected somehow to some other members, then those connections somehow they act as a support, or they are idealized as supports or joints. Okay, supports or joints. So in mechanical systems, for example, in shafts, so let's say we have shafts right here, and then let's say we have bearings. Okay, and let's say we have gears right here, or some power transmission devices. So because there's a lot of there's forces acting on these gears, for example, then because this shaft is being supported, this shaft is being supported by by the bearings, and let's say we also have the weight of the shaft. I mean, the weight of this gear. So somehow there's gonna be a reaction at the bearings. Okay, so there's gonna be reactions. Okay, so how do we analyze this reactions? Okay, so how do we analyze this? Okay, so how do we analyze the support reactions and joints? Then think about the just think about the 3D rectangular coordinate systems. So that means we can describe the support reactions and joints in terms of x, y, and z. Okay, but what about x, y, and z? Okay, so we have to think about forces and displacements. Okay, so for example, if we think about forces, that refers to the static function. Okay, static function of the support or joints. Okay, and for in terms of displacement, this refers to the kinematic um, ki- kinematic functions. Okay, of the joints or the support reactions. Okay, so basically the static function is to transmit the forces from one member to another. Okay, so from this beam, okay, so let's say we have forces right here. So in terms of static function, it's about transmission of forces, okay, from this member to this member. And in terms of kinematic functions, this is about the relative movement um, between two members. So for example, if we have a link, right? Okay, so let's say a slider crank mechanism, something like this in the kinematic of machines. Let's say this is a pin. Okay, so as this rotates, right? For example, this link rotates, then the the displacement of this? So it's actually preventing the, I mean, in this type of joint, it is actually preventing the relative movement between this member or this link 1 and then this link 2. But in terms of the static functions, then it's transmitting the load from this link to this link. Okay, so when we say forces, then of course we'll refer to forces, and of course this also includes moments. Okay, so forces and moments in x, y, and z. And for displacements, this is also displacements along x, y, and z as well. Okay, so right here in our lecture handouts, so we have here in figure 1-4, so the forces could be in terms of reactions along x, reaction along y, or will rather, since this is 2D, but the more a more complete one is, okay, so let's say this is x, y, and z. Okay, so we can have reactions, right? Forces along z, let's say f sub z. This one is f sub y, and then this one is f sub x. Or we can have moments, right? So right here, we can also have moment along x, and we can have moment along y, and this one we can have moment along z. But in terms of 2 dimensions, this is being simplified as this: the forces along x, forces along y, and the moment, right? That's the moment along z. Okay, so here we have six reactions, or 6 forces, forces and moments. But in terms of 2D, we only have 3. Okay, so that also goes true for the displacements. Okay, so we can have displacements. We can have displacements along x, right? So let's say this is x, then this is y, and then this is z. Or we can also have rotation along y. We can also have rotation along x, or rotation along z. Okay, so right here we have let's say this is our x, this is our y, and this is our z. So it can translate along x, or it can translate along y, or rotate along z for 2D systems. Okay, so there's actually a lot of supports and joints listed in textbooks for both 2 dimensions, dimensional systems, and 3-dimensional systems. But for us here, we'll just focus in the most common 3 that we'll encounter, which is the fixed support, the pin support, and the roller support. Now, I guess I'll continue this discussion in the next video.